This lesson is on comparing two linear equations. So lately you've seen only one in a word problem, and now we're going to see word problems that involve two linear equations. So we're going to look at that first, and then we're going to see how to solve graphically and using a table of values. And we're going to also see how we can do this solving it algebraically by something called the comparison method. Just a reminder of a few things. As always, y equals ax plus b. This is very important. This is the basis of our unit, where a is the slope, the rate of change, or the rate. B is the initial value, the starting value, or the y-intercept. In word problems, you need to determine what is the independent x variable and the dependent y variable. So keeping all of these in mind, which you've already seen because you've seen some word problems, but now we're just going to be doing it with a little bit more. We're going to start this whole lesson with an opening question. Fred and Barney are running to Bedrock. Fred runs 2 kilometers per hour and starts 20 kilometers away from his destination. Barney runs 6 kilometers per hour and starts 10 kilometers from his destination. My two questions that go with this situation are, when are Fred and Barney at the exact same distance? How far are they when they are at the same distance? So how do we start this question? We did a recipe for the last PowerPoint. Now I'm giving you a new one. So here's the preview of our recipe for this lesson. First, make two linear functions. Second, identify what our variables x and y will represent. And 3, you're going to have to solve the question using one of 3 ways: with a table of values, by graphing both functions, or algebraically. For the sake of this question, we're going to only look at table of values and graphing. So I'm going to keep our question here at the top so that way we can see how to start. So we know what Fred's situation is and what Barney's situation is. And now we're going to make a function for each. So if Fred runs 2 kilometers per hour and starts 20 kilometers away from his destination, your a is 2 and your b is 20. So this is Fred's function. Barney's function is, well, he runs 6 kilometers per hour and he starts 10 kilometers away from his destination. So a is 6 and b is 10. And our rule is y equals 6x plus 10. In this case, x is time, as always, h or hours, and y is distance in kilometers. So keep that in mind as well. So x is our time and y is our distance, how far they are. Now, how can these help us answer the questions, when are Fred and Barney at the exact same distance, and how far are they? What can we do with these functions to help us answer these questions? We're going to solve this question using a table of values first. Now, keep in mind Fred's function. Because we're doing a table of values, let's make a table of values for Fred. So I just went up by 0.5, and you'll understand why in a second. But in the end, you'll see everything. 1 is at 22, 1.5 is at 23, and so on, in terms of hours and kilometers. Then you have Barney's function, and that is what we just found. And let's make a table of values for Barney. Now take a second and look at these table of values. Do you see anything that might be the exact same thing? I have 2.525 and 2.525. That's kind of important. What do you think this means? Now before we answer, now let's look at the graph. If we are to graph these two functions, you'll notice that they intersect, but they intersect at a point that's very particular. 2.525, kind of like our table of values here. So again, think about it. What do you think this means? This is called the point of intersection, which we found using the table of values and now with the graph. So how do you think we can answer our question? We have good evidence from our table of values and graph what the answer is. Both functions meet at the point 2.525, and keep in mind x is time, y is distance. So Fred and Barney are at the exact same distance after 2.5 hours. So at 2.5 hours, they're at the exact same place, which you can see from your graph. And not only that, but where they meet at 2.5 hours, they are 25 kilometers away. So that's what this means. So when you're asked to compare two functions, you're essentially trying to find where they intersect, where they come together. And in this case, we have a good question and answer saying both functions meet at this point where x is time and y is kilometers. Now I want you to try this question by yourself, knowing that we did it with a table and with a graph. Ancients buried treasure on Easter Island where the path of two Maori statues crossed. Statue 1's path starts at coordinate 80 and has a slope of -1. Statue 2's path starts at coordinate -2, -10 and has a slope of 4. Where is the buried treasure? And remember, where the two statues cross. Here's your recipe. I would like you to make two linear functions, and then I would like you to solve the question with a table of values and by graphing. So do both. So here's what the question tells us about their path. So statue 1 starts at this coordinate and has a slope of -1, and statue 2 starts at coordinate -2, -10 and has a slope of 4. The rule, if we know that the slope for statue 1 is -1, we plug in the coordinate xy to solve for b. So the rule for statue 1 is y equals -x plus b. For statue 2, we're going to do the same thing. They gave us the slope, it's 4. We're going to plug in -2 and -10 into our x and y. Solving for b, we get -2. So our rule for statue 2 is y equals 4x minus 2. Now we can go on and see where they cross. Where do they intersect? I also want you to note that in this case, it doesn't matter that x is time or y is kilometers, because we just want to know where the paths cross. There is no specific given title for x and y in this question. If we do a table of values, you'll notice, if you did this correctly, that at x is 2, you have the same y's here. So this is our first indicator. And if we graph it, you'll also see that they meet at the point 2, 6. And so remember that this is called the this is called the point of intersection. So after doing our table and after graphing it, we can conclude that the buried treasure can be found at point 2, 6. Now that you know all that, another more effective and perhaps for you time-saving way is to find where two functions intersect by using algebra. Let's go back to our first question about Fred and Barney. We had this for Fred and this for Barney, and we had to find our table and where they intersect. So basically we need to find when the y values were the same as the x values. That's essentially what we were doing. To solve algebraically, we must just make the functions equal to each other and solve for x. Answer the question, when does y equal y? So this is Fred and this is Barney, and we want to make y equal to y. So we take Fred's function, 2x plus 20, and we take Barney's function, 6x plus 10, and we just make them equal to each other. And then you solve for x. So you would subtract 6 on both sides, and you would subtract 20 on both sides, and you get something like this. You divide by -4, and you get that x is 2.5. Looks like we're on the right track, considering we already know the answer to this question. But now we're missing something. We have x, but what about y? So we just solved that x is equal to 2.5, but we still need its partner, y. So what you're going to do is you're going to take either Fred or Barney's function, it doesn't matter which. You plug in your answer for x and you're going to solve for y. So here's Fred's function, but we already know from the last slide that x is 2.5. So let's plug it in, and we get that y is equal to 25. Looks like we're on the right track. And I'm just going to show you that you could have done the same thing, but with Barney's function. Here's Barney's function. You know that x is 2.5, so you're going to plug it in. If you solve for y, you get the same thing. So in this case, x is 2.5 and y is 25, and that's exactly what we got at the beginning of this lesson, but using the table and graphing. If this is your thing, this could be a lot easier for you. Before we move on to another example, I just want to go over some vocabulary with you. When we have to work with two functions, we call this a system of equations. So not just one equation, two. So we say a system. And when we make y equals y like I just did with Fred and Barney, this is called solving algebraically through comparison, because you're literally comparing the two functions, or we call it the comparison method. Now it's your turn. Solve the same question algebraically and see if you get the same answer that we found before. So you answered the question of two Maori statues that cross, and we got a certain coordinate. But now I want you to do the same thing, but algebraically. So remember, comparison method, y equals y. First step, solve for x. Second step, solve for y. So if you were to do this, you make negative x plus 8, equal to 4x minus 2, and that's what I did here. And then you bring your 4 over on one side and your 8 over the other side. It doesn't matter what you decide to do, but in the end, you get that x is equal to 2. And then you take it in either statue functions. If you take your x into the first statue, you get negative 2 plus 8, which is 6. And if you wanted, you could have done it to statue 2. X is 2, so you plug it in here, and you get that y is equal to 6 yet again. The answer is 2, 6, and that's what we got at the beginning of this lesson. So now, I would like you to practice the comparison method for systems of equations. I will be giving you a handout to complete, and you're just going to have to solve two linear equations just algebraically. We're going to stop the table values and the graphing for now. We're going to practice your algebra.